Hi everyone. So my name is Shilpa Lahoty. I'm a software engineer at Khoros, based out of Bangalore, and I work in the search team. So Rahul is the principal engineer over there, and today we will talk about Elasticsearch, but more specifically indexing part of it. So our agenda looks like first we'll talk about Khoros community, and I'll give an example of a customer community website. I'll walk you through that, and then followed by a brief introduction to Elasticsearch, and then we'll discuss the indexing design with ES7.x. So we are using currently a very old version of Elasticsearch, which is 1.7. So the whole process of indexing design, we came up keeping all the breaking changes in mind. So we'll discuss more about that. So since we were using a very old version of Elasticsearch, which is a 1.7, so many out of the box feature implementation we had to do, which was inbuilt, like highlight, prefix, search, synonym search, etc. So it was high time we moved to the latest version. So more than 500 Fortune companies use our community platform. So Spotify, Atlassian, and Airbnb is just like just to name a few. So what are community? So in layman terms, if I have to explain, I'll just say it like it's like a Q&A platform, more like a Stack Overflow, Quora kind of thing. So uh, so we so user can post blogs, post articles, give kudos, like dislike some post, or like in general, like how a Q&A platform looks like. So let me show you how the Spotify community looks like. So this is a Spotify community. And so the numbers you see over there, the number of online users, the number of solutions, the number of members, registered members. So all these numbers are fetched from Elasticsearch. And the different post of a particular category, for example, health post, music chat post, ideas post, all these numbers are also fetched from Elasticsearch. We have these are the forums, and these are the latest post, and all these things like number of comments, all this thing, everything is, I mean, fetched from Elasticsearch. Everything is backed by Elasticsearch. So I'll go back to the slide now. um, yeah, sorry. So I mean, that's how a generic community looks like. So now I have a QA site with me where I'll walk you through that how we create a post, and how we like how we search, and we support different type of search like user search and normal messages search. So how do we do that? So 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 this is what the QA site is. So here I have created a post board called ES Meetup. So I'll try to compose a message over here. So as you see, like as I'm typing, I do get a suggestion that if we have a similar post with similar kind of subject or body, this is also backed by Elasticsearch. So I'll just post this message, and when I go back to the community, so when I search for Elasticsearch, I get all the relevant articles, and it's been highlighted the matched keywords. Now this is an auto suggest. When I go to SERP, So there are like two results. So we also have different, so this is the messages. Let's say if I want to search, like I have registered myself as Shilpa. So if I want to search with user with the name Shilpa, so this is how it is. So coming back to the slide now. So apart from this, we like there. So these are like very few places which of use cases of search which I have shown in our community. So we also have a homegrown query language similar to SQL, which we use for searching messages based on subject, body, tags, different fields, basically, etc. And so, like I showed in the example of Spotify, the total count is also fetched. I mean, the result is fetched by Elasticsearch. And so, and now I want to just give you a picture of how much data we store in our Elasticsearch and what's the bandwidth basically. So we have a number of communities which are powered by the Khoros community platform is more than 450 plus. We have more than 15 Elasticsearch clusters, both in data centers and AWS. And we also have the number of index document is like more approx 700 million. And the number of approx queries is 1 lakh per second. So these are just a few numbers to make you all understand like how much data and what's the QPS of our search engine, I mean in our community. So now I'm sure everybody knows what Elasticsearch is and everybody is well aware of its use cases. I'll just give a brief overview before starting off. So Elasticsearch consists of a node, like one node or many. And in each node, we have a primary shard and one or more replica shards. So while creating the cluster, we have to specify the number of primary shards. We can change the number of replica shards on the go. And so any write we want to make, like whenever we are posting a message or anything, so any write goes to the primary shard and it's been replicated to the replica shards. And like if a cluster looks green, if everything is well, like all the primary or replica shards are fine. But if one of the primary replica shard is missing, the cluster goes yellow. And if one of the primary shard is like goes down, then the cluster is red. So this is just a like very brief, because I don't want to shift the focus from indexing, which is our main focus over here. So I just gave a brief intro of to Elasticsearch. So how does search work? We all know like there are two main operations involved. One is indexing and one is querying. So from community, let's say if I have to let's say if I have created a post or something, so community index this that post to Elasticsearch, and if I have to query something, then the community fires a query to Elasticsearch and fetch the results. So we stored information of entities such as messages in ES index. So we had different entities like messages, users, etc. And every entity data is stored in a different index. What I mean is like for every type we have a separate index. We have a separate index for messages, separate index for users, like that. So again, this is just plain like brief overview. So like I mentioned that entities are indexed in Elasticsearch and they are done using JSON documents. And every index is associated with a schema which defines the properties of the field of the JSON documents. Say, so we have different fields for message index schema, like subject, message ID, body, tags, etc. And we also store with each field the type stored and other properties of that particular field. And schema can be updated over time. So similarly, we have a user index schema where we have name, login ID, email, etc., etc. So this is what it is. So now, so from a community platform, let's say if a user is creating a message with a subject, happy birthday Shilpa, with a message ID 1. So how it's get indexed in Elasticsearch, and how Elasticsearch, like when I'm searching for happy birthday Shilpa, how Elasticsearch uh, uh, returns the search results and all these things. So basically we have a very simple concept of inverted index, which Elasticsearch uses internally to help in the accelerate the search. So what inverted index looks like is, it's basically uh, so every word, whatever, like let's say happy birthday Shilpa, we tokenize it to happy birthday word Shilpa in 3 words. And in inverted index is nothing but it's a key value kind of store, where the key are the words, basically the tokens, and the value are the list of document IDs which contains that particular word or token. So when I'm trying to index happy birthday Shilpa, so it's been populated in inverted index as happy is present in document ID 1, birthday in 1, Shilpa in 1. So same way, likewise, when I'm trying to index another message, happy anniversary Rahul, this is how our updated inverted index looks like for subject field. So when I'm querying, let's say if I'm querying for happy, so what Elasticsearch will do is it will look up the inverted index and will look for the word token happy, and see that which all documents have this particular word, and it will fetch that result. So when I look for happy, I see that document 1 and 2 has that. So I return that as part of the result. So similarly, when I'm searching for birthday, it will look up birthday is in which document, and it's in present only in document 1, and it will return the document 1. So this is like how in simpler way how Elasticsearch maintains an inverted index of all the words that is being indexed in Elasticsearch, and helps in returning search results for a particular search query. So so these are the few points which I think so now I think we should talk more about so now, okay, yeah, I think I should pause now for some questions if you have any, or you can maybe if you have some questions or something, you can put it in the chat, and which we will take it later on. So I think, sorry, I'm so sorry. So I think Rahul can take over from here. So yeah. Should I stop sharing, Rahul?
Yeah, you can stop sharing, Shilpa.
Yeah, thank you all, and Rahul will take it from here.
So thanks, Shilpa. Thanks for setting the context for what is going to come and what is going to be a much more deep dive topic on how we do indexing. So before I go ahead, I just wanted to give a small anecdote. So if you see in the background, there's a rainbow, right? This photo was actually taken by me on the Rupkund trek at a height of about 16,000 feet. And there's a reason why I put this photo. If it's not easy to get to that 16,000 feet, like you just can't do it like in a day because of acclimatization, right? So it's like you first reach a camp at 8,000 feet, then you stay there for a day, you get acclimatized, and then you go to the camp at 10,000, 12,000, and eventually you reach at that 16,000 feet. And every step you take, it keeps getting harder and harder and harder. But finally, when you reach there, you're like, wow, I mean, we did this, we built it, right? I mean, so in a very similar way, if you look at the way we have come up with this design, we had like a bunch of requirements and we couldn't tackle like all of them in one go, but we took one at a time. And then we kept appending again, refactoring, and that's how we have come up with the final design. So the idea of this presentation is to walk you through the thought process behind how do we design a complicated system looking at a myriad set of requirements, so this process can sort of be replicated for even while designing other systems. So that is the first point I wanted to talk about. I want to just call out. The second thing is I will be pausing for question and answer like at every after we address each requirement. The reason being, it keeps, if you don't follow if you don't understand, let's say what we're doing at one step, understanding the second step might be a bit more challenging. So I want to ensure that there is clarity for at each step. You have enough clarity before we move on to the next one. And the third one I want to call out is I have used message entity as a reference over here. Like Shilpa has said, we have different entities. We have message users, and for each one of them, we have a different index. So although we'll be using message over here, we have applied the same design for other entities such as users, nodes, etc. Okay, so let us look at what the indexing requirements were for Khoros. So the first one is a very basic requirement. Whenever we create a new index, all the existing data from our existing permanent data source, which is MySQL, should be read and they should get indexed into Elasticsearch. The second one was these messages and these users, they can keep getting modified over time. So whenever they are modified, they have to be again indexed into Elasticsearch. The third requirement is a slightly unique one to Khoros. So we generally have like multiple Elasticsearch clusters, like we call it the 15 Elasticsearch clusters. And sometimes what may happen is that, let's say a community has an index on one particular cluster, that cluster might actually get overloaded. So we may want to temporarily use another cluster, like create a new index, use another cluster, and then again switch back to to the older cluster. So there's a use case where we might switch between indexes, between clusters, and we have to ensure that when we switch indices on different clusters, if it comes back to the older cluster, the data has to be updated. Like any new data which got created or any data which has been modified in the interim, that gets updated on the older index. The fourth requirement was that we have multiple application nodes for the community. For each, for example, for each customer, we may have about 4 to 5 Java processes running, which are serving the community. These also actually process the documents and then index into Elasticsearch. So we wanted to ensure that the load which gets added because of reading the data from MySQL, processing it, and building the ES docs, that is distributed uniformly across all the application nodes. It shouldn't be just one of the nodes is doing all the processing. And then the fourth requirement was the schema version change. So like Shilpa said, we have something known as the schema version. What this indicates is, like, let's take, for example, the message entity, right? Today, it may just have 2 fields, subject and title. Tomorrow, we may have new requirements to add tags and attachment. So this is indicated by something known as the schema version. And whenever we add new fields or modify fields, we modify the schema version. So the indexing system should be smart enough to identify that, okay, we have changed the schema version, and so we need to re-index all those documents for which the schema version doesn't match. And then the last requirement was support for DLQ. So there could be instances where certain messages have data which is corrupt, or messages which cannot be indexed for some reason. In this case, there is no point of going on retrying to index those messages. So we needed some way to track those messages and pause it from being continuously retried for reindexing into Elasticsearch. So I'll go to the very first requirement, which is the basic requirement that we want to index all the existing data. And this is a straightforward thing that we could actually do. So any one of the app nodes could just read the messages from MySQL in, let's say, batches of 1,000. And as it reads, it can index it into Elasticsearch cluster. Right? So this would address a very basic requirement that all existing data should get indexed. But there are limitations to this, right? How do we track and reindex new messages? Like I said, there are multiple nodes, and when we add a new message or when we create a new user, that information could be done on any of the application nodes. But if only one node is actually sort of indexing and doing it, then we need some way of informing that node that, okay, there are new entries to be indexed or modified entries to be indexed again into Elasticsearch cluster. On a similar note, if, let's say, Elasticsearch cluster goes down and then it comes back after a while, any messages that have been modified during that interim, they have to be reindexed, right? So we need to track them as well. So we have to see, how do we address these issues? The way we came up with this is to have a new table. And in that new table, we have added a new column known as the status. The status bit is actually it sort of says that, okay, this message, let's say the status bit is 1, it says that, we have to reindex this particular message. So just showing everything pictorially, this was the existing part where, one of the app nodes would keep reading the existing entries and index into Elasticsearch cluster. But then we have an additional table for tracking the dirty bits, right? Like what messages need to be reindexed. And if any other app node actually, like let's say if any other app node has a message on modified on it, it would mark the bit as one, the status bit as one in this table. And the node which is actually reading the data and then processing and sending to Elasticsearch cluster, it could just query for all those messages for which the status is one, and then it could send it to Elasticsearch cluster. So this way, we don't need to like reprocess everything. We get only the entries which are modified, and then we can send it to Elasticsearch cluster. So that addresses our second requirement that whenever entity is modified or created, we should again reindex it into Elasticsearch cluster. So I'll take a pause here. Are there any questions so far with respect to this design?
Yes, I have a question. So how are you actually updating this particular MySQL table with the column, whether it is updated or not?
So this one is like, it's a direct MySQL table. And so there's in one, we have the actual message ID with all the message data, right? Like the subject and the body. Then we have a newer table where we add a new column. So the application, so whenever, let's say you modify a node, it can go to modify a message or create a new message. It will go to any of the application servers. So that would just make a MySQL connection. And because it has the corresponding message ID, it could just update the entry in the table with a simple update command.
Okay, so is it something like a kind of virtual log kind of thing?
No. It's a direct, no. So it's just a direct connection to the tape. So we basically batch it and then we send it across. And
okay. So it is something like once you update the actual message, like in the table, messages table, so you'll also insert a record into the other table, right?
Yeah. We'll update the record over here as well.
Okay, got it.
So Rahul, there's one more question, like how do you read from MySQL and index to ES using Logstash or Java or Python client?
No. So right now we just use a regular Java client. We use the Elasticsearch 7.x Java client, and so we have the application nodes which actually read all this data, does this combination and build the ES doc, and then we send across the ES docs using Elasticsearch Java client. But we use bulk messaging because like if especially there's a huge number of messages, we can't do single messages, so we send across a bulk call.
Okay, there is one more question, like is MySQL a single cluster, a single machine or a cluster?
So we have multiple instances of MySQL. I don't think MySQL is a cluster, but because we have like multiple, I would say like multiple MySQL nodes, certain set of communities would be talking to one MySQL cluster. So in a way, we are building like some sort of load balancing. But internally, I don't believe MySQL is actually a cluster. We're not using the MySQL cluster package. That's what you're referring to.
Yeah, I think one last question that I saw here, is from Aditya saying, did you implement AAD? AAD means, I believe, Active Directory?
No, we don't. No, so we are not authenticating against domain users over here. So this is against the community users. And I don't know if he's talking of like AAD in the community side on the Elasticsearch, but Elasticsearch is more IP-based because ES is not exposed directly to customers. It's more of IP-based security that we have. We've not included any kind of AAD integration.
Okay. I think you can continue, and I'll see if we can.
Yeah. Thank you. Okay. So the second requirement being addressed, but again, like I said, it's not all happy go merry, right? So we still have limitations. So this is the one which I was talking of, which is a bit unique. I wouldn't say unique, but something which maybe not everybody may have a use case of. This is where we wanted to, have the feasibility of switching from one index to a new index. And then, if we come back to the older index, again, all the information gets updated. So how are we doing this? We use a very simple concept as known as timestamp. Okay, so whenever the application node sends it for indexing, like it builds a ES doc for a modified message and then sends it for indexing, we maintain a corresponding timestamp column, like as to when it was generated and sent for indexing. So now let's look at this example. Okay, let's say we are right now on index, let's say we're on index 1, which, okay, and we get these three messages, 123, 20, 34. These three are indexed. And immediately after that, we move to the new index, okay? And then there are these three messages which come in, 67, 123, and 83. These three, we will update the entries in DB table with that status, and then we'll also update the timestamp column, and we'll send it for indexing in the new index. Now, when we revert to the older index, these three messages will be missing, 67, 123, and 83, right? So how do we figure out that we have to reindex these things? What we do is a very simple thing. We query Elasticsearch to get the max timestamp of all the messages that are indexed in the particular index. So in the older index, the maximum message, like the maximum timestamp would actually be this entry, 178993100, right? And then once we get that value, we query this table for all the records that have a timestamp greater than this particular value. And that will tell us that, okay, these all are the entries that which have got added after, like in the interim, and we need to reindex all of these. So starting from this timestamp, it will again, when you switch to the older index, because it will not have all these entries, it will look for all entries with timestamp greater than this, which is all these three, and then send it to Elasticsearch for indexing. Again, just showing that pictorially the flow. We have a new column for timestamp. Whenever the app node has to index let's say it has to index a message, it will first update the timestamp to the current timestamp, and then it will send it to Elasticsearch cluster. That's a standard flow. And whenever we have to, like again, let's say a node gets booted, or we switch to an older index, it will get the max timestamp of all the messages in ES, and then it will search for all those messages which have timestamp greater than or equal to that max timestamp, and then it will reindex those. So this will ensure that, even if we toggle between different indices, once it comes back, it looks at what the backlog is based on the timestamp, and then it will reindex them. So that addresses our, our next requirement. I'll again take a pause here. Any questions on this logic that we are using?
Maybe not at the same logic, but then there are a few more questions from Abhilash and Ravi Siddhant. So I'll quickly go. So what is the need to switch between multiple clusters? Did you consider cross-cluster replication?
Yeah, even if we look at cross-cluster replication, right? I mean, so basically, like I said, one of the needs could be like we want to move, one of the clusters is loaded. So it's like we don't have a single cluster for all the communities. So it's like if you have 500 communities, 50 communities could be on each cluster. And then sometimes you may realize that one of the communities is actually receiving more load. And so we may want to move to another cluster. And then, yeah, we can move to the other cluster. But let's say there are some issues, we always want to move back. So for that's the requirement for moving between different clusters.
So,
and even if you do cross-cluster replication, we still have a sync up sort of thing to do, right? Let's say we copy from cluster 1 to cluster 2. There is a snapshot of where it's copied. But what about all the new messages that get created in the interim? We still want to do a catch up on that. So even in that case, this is something which will be handy.
Okay. Yeah. So one more question is like, how do you size the bulk request? Is it by size of bulk payload or number of docs in the bulk request?
Actually, three things by which we size. So it is number of messages, it is the size, and it is the time. So I think the size limit we used is 5 MB. I don't remember, it's around 5 MB. And then probably the bulk size is around like 1000. And then, we have a time limit of like maybe some 10 seconds for which we wait for newer messages. So based on all these three factors, it will proceed. So the idea is we just don't look at one metric for deciding how long to wait before we fetch the next batch or come out of the loop.
Yeah. One more question is,
by the way, I think Elasticsearch client supports this out of the box. The bulk, the client has feature for all this.
Yeah, with all whatever Rahul is saying, that and all is supported actually, right, as a parameter. So how frequent are these queries, Rahul?
Which queries? I mean, how frequently do? So this is all on the indexing side. So indexing. So the thing is, like, we have communities which have like 20 million. I think The biggest one we have right now is like around 100 million documents. So whenever there's a schema change or something like that, at that time, we need to reindex all this bulk of 700 million messages, and that's where it comes. The schema change could occur like, I don't know, maybe like once in 3 months or so. And apart from that, we don't have like the entire set of messages to be reindexed, but every day we will get new messages which are created, which we have to keep reindexing. I don't have an exact count on how many newer messages are getting created every minute. But yeah, this design is mostly for those scenarios where we have to bulk index the entire set of messages for all the communities, right? So that is where this really scales and shines.
Just more like I actually asked that question, so I just wanted to understand more about it. You, like you said, whenever the schema is changing, you'll actually perform those queries. So my question was basically for the queries you mentioned about getting the max timestamp, and then based on that max timestamp, you're going to get the newer records which are changed. So if I understand correctly, that's something which is a pull-based ingest, right? So like, have you ever thought of like, not sure, but if you have thought of doing some CDC, like if you want to have real-time syncs, or probably if it is a batch approach, then it's fine. But just wanted to understand that.
So, yeah, sorry, so I didn't get your question correctly. I mean, now I understood. So the timestamp check happens like within every 1 minute. It's like every time it runs, it first checks if there are any messages to catch up. And that's not all a costly query, because all we have to do is, get the min timestamp from, get the max timestamp from Elasticsearch cluster and then query it in SQL. So that happens every 1 minute. And we index, all these fields are indexed. Like in MySQL, the timestamp is indexed. In Elasticsearch also, it's indexed. So that the query to figure out, like, are there newer messages to index is actually pretty fast. So this happens every 1 minute. Like every 1 minute, we have a check for doing it. So, and we are good with that real-time thing. The reason being, whenever there is a message, I mean, this is a bit into a lower level details, but whenever the message is modified or created, it actually first directly puts it into Elasticsearch, and then it puts it into this particular queue from where it is picked up. So even if there is a delay of, let's say, if you put into this MySQL queue and it gets picked up and there's a delay of, like, let's say 2, 3, or 10 minutes, we are still okay, because there has already been a direct call which has gone to Elasticsearch for that modified message.
Yeah, that makes sense. Thank you.
I think, Rahul, we can continue and further again take some more questions. There are questions coming in, but I think go ahead.
Okay. So I hope this thing is clear on why we are using the timestamp. Okay. Yeah. So now comes the other requirement, right? If you see in all the earlier things, we just have one of the app nodes, which is reading from the message table and then, like doing all this processing and putting it. And the reason for this being that, it's difficult to sort of do concurrency if we have, like, like do simultaneous processing if you have multiple nodes, like which batch of messages each of the nodes read. So that's a challenge. And there's an easy way to address it, right? We can just use a Kafka queue in between, and then we can have this one node just read the message IDs which are to be reindexed, and it can push it to the Kafka queue. And then, the individual nodes can read it from there and then process it. So just to show this diagram over here, if you see here, each node can just read the modified messages. It can push to Kafka queues. And then each of the application nodes, they can read from one or two of the Kafka queues, and then it can process and push it to Elasticsearch cluster. But there is a challenge with this. The challenge is basically around concurrency. Now, let's say you have a table, and these are the messages which need to be indexed, okay? And 123, 20, and 34 have gone to node number, like let's say to first node, okay? 67, 123, and 83 have gone to the second node. Now, let's say the first node has indexed 123 and 20. Before indexing this 34 message with this particular timestamp, it has crashed, okay? But the second node continues to index 67, 123, and 83. Now, if let's say we switch index or whatever, and we come back to this older index, or we restart the nodes, the first thing that this particular node does is it will try to get the max timestamp of all the ES messages in ES, right? Because that's from where it will continue to fill for the catch up. Now, if it does a max timestamp over here, it will get this particular entry 205, and it will try to look for entries which are greater than this and then reindex only those. In which case, this particular message will be lost. It will never be reindexed. So how do we address this, right? The way we address this is we basically add a new column and we cluster the messages into partitions, and we ensure that all the messages belong to the same partition always go to the same app node. How do we do that? We do that using Kafka, where in Kafka we have this option where we can give a partition ID like a key, and it will always go to one Kafka queue. And because one Kafka queue is always processed by one partition, by one app node, we can be sure that the same app node will continue to process this particular partition. So let's come back to this example, right? The first node gets, let's say, this particular partition 123, 20, and 34, and it has processed these two messages. It has crashed. It has not processed 34. The second node gets these three messages. It has successfully processed all of them. Now, the challenge is we just can't do a max of all the timestamps, because then we'll get this timestamp and we'll start indexing for messages greater than this timestamp. So it will be missed. So we have modified the query to get the min of the max timestamps from each partition. So in Elasticsearch, the entries that have been added by the first node are these two entries. The max timestamp over there is this one, 169343, right? And for the second partition, the max partition is 2056931009. Now, if I do a min of these two, I will get 19634. So now if I take that as the threshold, and if I say kindly reindex all the messages which are greater than, which are greater than this particular value, then it will automatically reindex 34. A flip side of that is it will also index 67, 123, 83. But that is something which is acceptable, because this is a very corner case and there might not be like too much of lag between these two. So at the cost of some additional reindexing, we are fine to take that load to ensure that there are no missed messages, like data is not out of sync between the primary DB and the Elasticsearch cluster. And maybe I'll just pause here and let me just finish the next slide and then I'll take the questions. So just talking of the same thing pictorially, we have the partition ID, and every message we map it to a particular partition. The way we do it is we do a murmur3 hash and then do a mod 256. And then this particular node, when it needs to figure out what are the messages to be reindexed, it will get the min of all the max timestamp aggregated by the partition ID. And then it will send all those messages for reindexing to the Kafka queue. Again, when we push the messages to Kafka queue, they are indexed by, they are partitioned based on the partition ID, which means that app node 1 will only get one of the partitions. Like one partition can't be processed by multiple app nodes. And that way we ensure that there is no concurrency conflict. All messages belong to a particular partition are always processed by the same app node. And when we are writing to Elasticsearch, again, we have to we add a new field for partition ID and we write it to Elasticsearch cluster, because this information is useful when we need to figure out what is the threshold timestamp after which I need to reindex all the messages. So this is probably the most complex piece in this presentation. So I'll just take a pause here, and I'm sure there'll be questions around this. So I'll take them.
Yeah, I think there are a few questions, maybe not yet related to this one, but one question from Shalini is like, if new mapping need to add to existing index, the data is lost, how do you manage that?
Come again?
So yeah.
The Shilpa, you want to? Yeah, take it.
Yeah. So let's say if I have added a new field or something like that. So for that case, we have a major version, minor version. So we do, like when we change the minor version, so it triggers a reindexing of the whole document. And if it's a breaking change, let's say I'm changing the type of the analyzer or something, so it's a breaking change. In that case, like we create a new index and then we reindex the whole document from the older index to the new index with the updated mapping.
Yeah.
I hope that answers your question.
Yeah, I think we'll go ahead and like if they have more questions they can ask. And then one more question is like, does this design support indexing of multimodal data like images, attachments, and videos apart from text?
Right now, our requirement is more around text. So it's all basic text. We have different indices for different types of data, but we've not yet explored there's nothing specific in this design which limits us from adding images or something. But our system doesn't have a requirement for indexing messages. Like when we have attachments, like text attachments, we pass it and then I think we add it to Elasticsearch to make it queryable. But directly images, I don't think we're adding.
But one more question is like, who makes the direct call to ES?
So in this case, the application nodes make the direct call to ES. Yeah. Like while reading, one of the application nodes will read from Elasticsearch, and while writing it, the application node. Like we did consider the possibility of using something like Logstash in between, where we could, send, like we have like these multiple communities, and we could send all the messages to be indexed to the Logstash, and then we could sort of have more control over, like what kind of, how much threshold to have, and you could have different kind of priority based things, right? Like certain set of messages from all the communities, certain type of messages from all the communities could be prioritized over the other type of messages. But we didn't have a very strong use case for it. So we were like, let's start with this. And then when we actually have a requirement, it's pretty easy, right? Like we have a Kafka queue between these two. We can always add a Kafka queue between, or let's say Logstash between Elasticsearch cluster and the app nodes. And the data from that could be redirected to Logstash. But like I said, we don't have a requirements right now. The app nodes use are very good ES7.x Java client, and then they directly do bulk calls to Elasticsearch cluster.
So how are the partition IDs are assigned dynamically for the messages?
So the partition IDs is actually murmur #3 of the message ID, mod 256. So why did we select murmur #3? Because it's fast and it generates a uniformly, like a pretty uniform hash. And why did we generate mod 256? Because we could store the partition ID in 1 byte. So either in Elasticsearch or in MySQL. So, and I don't think we'll ever have the use case of, actually, we won't have a use case using more than like 8 or 16 partitions, but we did use 256 just to make it scalable. And this is always constant. For a given message, the message ID never changes in our system, and therefore the partition ID will never change.
So how does the app nodes pick messages belonging to one partition? Maybe it's Kafka.
The app node doesn't pick messages belonging to one partition. They are already assigned. So this node, right, this single node actually decides that, okay, these are the messages to be indexes, right? The message IDs to be indexed. It also has the partition information. Then based on the partition information, it will push to a particular queue. And that message, because the partition ID doesn't change, it will always go to the same queue, right? Then the app node, if it connects, each queue in Kafka, it's called a partition, right? That can be processed by only one app node. So when the Kafka client consumer runs over here, it just connects to, like, let's say maybe this one connects to these two partitions, this one connects to these two partitions, and then it just reads the messages, process and sends it. The app, these nodes just don't worry about, dude, like, am I supposed to process this or not? All they do is like, okay, I have connected to certain topic, certain partitions. I just need to read the messages, and it says assured that, you know, the producer is actually ensuring that messages belong to the same partition, always going to the same queue. So that's how we do it.
Great. I think that's it for now. I mean, Rahul, you can go ahead and finish it off or something.
Cool. Okay, right. So that's one of the, you know, it's actually something which we didn't have in our existing system, and it was a new implementation as part of, you know, like ES7.x, where we saw a shortcoming in our existing design and then updated. So now comes the next requirement, right? This is something which people have asked. How do we, like, let's say we add new fields, we remove fields. How do we ensure that, they are re-indexed? So we have a column known as we add another column known as the schema version column. And what this does is whenever we generate the message to be indexed into ES, we link it with a particular schema version. So it's possible that right now the schema version is 56.4, okay, and we have like all these messages which are which we generate based on that schema version and then index into ES. Now, if we upgrade to 56.5, we just check against the message against this particular table. What are the messages which have a different index version, and then we again send them for indexing. So in this case, if you see, it may so happen that all of them are 56.4 initially, and then the node might realize that, okay, fine, the schema version got upgraded to 56.5, so I need to reindex, and it might have reindexed, like let's say this first, second, and fifth and sixth messages, and then maybe the node might crash, right? Or it might come back later. But at the next thing, when it again queries, or if you're doing batch, right? To the next batch, when we look, it will see that these have already been upgraded to 56.5, and it has been pushed to ES. But these two are still 56.4, so it will just fetch these two, and then it will process this. So this way we can ensure that we just ensure that whenever the schema version is modified, is changed, we again reindex all those messages, and we do it in a way such that it's resumable. Like whether we do it in batches or even a system goes down and comes back, we don't have any issues with that. And yeah, the last one is around dead letter queue. This is a straightforward thing. Like I said, there could be instances where maybe there is some data corruption or something like that, and some messages could not get indexed for whatever reason. So there is no point of going on trying to reindex those, right? So in that case, the app nodes actually, whenever they're trying to index, if it fails, it will just mark the status to 2 in this particular table, and then then when this node actually tries to fetch what messages need to be reindexed, it will not fetch those with status 2. The ones with status 2 are only reprocessed whenever we do a schema version change. That is, whenever the schema version is, because then there's a possibility that it's worth trying again reindexing, right? Maybe some field type has been updated or something like that. So just displaying, again, talking of that pictorially, we have added a new column for the schema version, and whenever we have to query, we look for all those entries which have outdated schema version, can do it. Similarly, there's the status field has a new value 2, which we call the DLQ value, and these particular nodes, whenever they try to index, if it fails, it will just mark the status column as 2, so that whenever the node has to decide what messages to be reindexed, it will ignore those with status 2, and then it will only take those with status 1 or status 0, and then it will push it to this particular Kafka queues, and the nodes will continue to process it. I'll pause here. These are not, not very complicated, but I'll take any questions if they are there here.
Yeah, I just want to add one more thing to what you have said, Rahul, regarding the versioning. I think there is a version semver field, semantic versioning field type coming in the mappings.
Okay.
Like a field type. I think right now we have some 25 plus field types, like all the string, keyword, etc.
Mm-hmm.
There is another mappings improvement itself is coming, the API improvement. Okay. So I've pinged that GitHub link in the chat. Okay. And then there is one more question from Gaurav, as Elasticsearch has the ability to be schema-less, what is the advantage of explicitly providing the schema? Yeah.
So I think let's say we are querying or something. So the way we do it is we have the corresponding schema types and all that defined in that app, right? So we can always, if we have a well-defined mapping, we can always assume the case that this particular schema is of a particular data type, and then we can do it. I think we could probably consider the possibility of doing it schema-less, but then it would be we don't know what all fields are there, and there could be random fields which come up. So we've not. We could probably consider going schema-less, and then sort of for newer entries or something, we could want to, like just add it. But what about those cases where we are maybe deleting some fields or we are modifying the types of some fields? That has happened a couple of occasions. So in those kind of cases, we still need some way to track and we need to reindex, right? So that's where we still need this.
Yeah, adding to what Rahul has said, like in general, so if you have probably like no, you don't have mapping and you go schema less, and then Elasticsearch would dynamically create mapping schema. It's called dynamic mapping. And when you are searching on something which you want to be specifically written in a specific time, and you want to ensure throughput and do all of this, then I would definitely recommend go with a schema. So you know what field type is what and how you want user to be searched, because you're the one who are sending the query. So you know, and you design for the system, and then that is like ensuring and getting more juice out of that, the system, rather than like just letting the system decide whatever it wants, which might not be a right approach all the times.
Totally agree with you, Arvind. I mean, like, especially there are some types which are like, day, which are long and all that. And maybe Elasticsearch is smart enough to infer that, but then, you better to be explicit rather than, hope that it does its best.
Yeah, Elasticsearch just does the best case optimization, but then what is the better or the identical situation. So you will choose the right type. So there is one more question, Rahul and Shilpa.
Yeah.
Say like, what is the average time of a message in the community?
What does that mean? Like, what is the average time to query?
So how much time this record remains in the cluster or probably in the queue?
Forever. It remains till it's deleted. So till the message is deleted, it remains in the cluster.
Okay.
It's 12 o'clock.
Yeah.
Thank you.
Yeah, that's great. So there's one more question also, like, have you tried with Solar Server?
No, so we used Lucene earlier and then we moved to ES. We're not expert much on Solar.
Okay, great. So I think that's the question. Like, okay, we have one more from Shalini. Like, can Kibana be used for import export indexes? Have you used Kibana to do any of this?
We not for this. So Kibana is more of a front-end visualization tool, right? So we do use Kibana internally. Like, we have a lot of metrics, aggregated metrics, which we push to Kibana and then we query over here. But here the use case is more for free text search for the end user. So we don't have Kibana tied into any of this, and I don't know how it would like the amount of processing that these app nodes do to retrieve the to build the ES nodes. I mean, that's all complicated. So I don't know and it has to be like on the fly, right? So I don't know how Kibana would actually even fit into this picture. But maybe we could use it for some visualization, but right now we don't.
Yeah. So there is one more question from Manoj. Can ES itself not act as the main store for the messages? Why do we need MySQL DB?
Yeah, because it's different, right? I mean, basically ES is more like what do I say? It's like a denormalized system. Like, you can't have like relational kind of thing. And it's also like, for us, this is the main data source. So it comes around the question like, Elasticsearch we use more as a cache or, like as a, for free text search. It's not, generally we don't use Elasticsearch for a primary data source, like especially if the data is very critical and all that, then we may have use cases, but like I said, how do we join? There are ways in which we can do Elasticsearch joins as well, but it's not very optimized for those kind of things. MySQL is where we want to do this cross-reference keys and then do it. So it's a different search thing which provides. I think you can add more to this as well, I'm sure.
Yeah, I think quite a few users also use for data store capabilities, but the key here is like when you are using it like a data store to replace a RDBMS system, which is also very complex and does a lot of good stuff. So what happens is like you need to configure, the big backups and a lot of these things, which also is there. So, but generally people don't think of it a lot when it comes to ES. And that mentality should come where in an RDBMS system, DBA would automatically create disk backups, or there are automatic systems which automatically do all of this. So there is an thing for it. And then schemas and normalization, there are several things that people naturally know, because SQL and RDBMS systems are known right from when you're studying in college. NoSQL is a bit new, and then people might not be aware of all of these things, but I personally see many people use it for catalog stores in their e-commerce systems. There are companies in India where they use Elasticsearch is the only primary data store without using any other database, and they use it for their catalog search. So yeah.
That's interesting. I mean, like, at least for us, actually, frankly, I mean, the thought didn't cross through, because this MySQL database is something that we have been using for like 20 years, right, since the application is beginning. So just moving everything out of that to Elasticsearch would be a tough thing. So yeah, so it is, and consider that option seriously so far.
Yeah. So if you have any more slides, I think Rahul, you can cover. Other than that, like we can go.
Actually, yeah. So this what I've covered so far is like a lot of high level details, and there a lot of low level implementation, like how do we do what batch. I think somebody asked a question like how do we do it, on what threshold do you do. So there are a lot of low level details also, which probably is difficult to cover in the short meetup. Maybe it's a topic for some other next meetup, right? So thanks a lot. I mean, thank you, Arvind, for helping organize this. I mean, it was good, presenting this and reading about all these things, preparing, and I really enjoyed it. Hopefully, we'll have more of these presentations in the future as well. And I think this is like third or fourth one from Khoros. So yeah.
Yeah, thank you, Rahul and Shilpa.